The major functional parts in a digital computer are central processing unit, CPU, memory, and input-output. The main digital hardware functional units of CPU are control unit, arithmetic and logic unit, and registers. The function of the control unit in a digital computer is to initiate sequences of micro-operations. The number of different types of micro-operations that are available in a given system is finite. The complexity of the digital system is derived from the number of sequences of micro-operations that are performed. Two methods of implementing control unit are hardwired control and microprogrammed control. The design of hardwired control involves the use of fixed instructions, fixed logic blocks of arrays, encoders, decoders, etc. The key characteristics of hardwired control logic are high-speed operation, expensive, relatively complex, and no flexibility of adding new instructions. For example, CPUs with hardwired logic control are Intel 8085, Motorola 6802, Zilog 80, and any RISC-reduced instruction set computer CPUs. When the control signals are generated by hardware using conventional logic design techniques, the control unit is said to be hardwired. Microprogramming is a second alternative for designing the control unit of a digital computer. The principle of microprogramming is an elegant and systematic method for controlling the micro-operation sequences in a digital computer. For example, CPUs with microprogrammed control unit are Intel 8080, Motorola 68000, and any CISC complex instruction set computer CPUs. The control function that specifies a micro-operation is a binary variable. When it is in one binary state, the corresponding micro-operation is executed. A control variable in the opposite binary state does not change the state of the registers in the system. The active state of a control variable may be either the 1 state or the 0 state, depending on the application. In a bus-organized system, the control signals that specify micro-operations are groups of bits that select the paths in multiplexers, decoders, and arithmetic logic units. The control unit initiates a series of sequential steps of micro-operations. During any given time, certain micro-operations are to be initiated, while others remain idle. The control variables at any given time can be represented by a string of ones and zeros called a control word. As such, control words can be programmed to perform various operations on the components of the system. A control unit whose binary control variables are stored in memory is called a microprogrammed control unit. Each word in control memory contains within it a micro-instruction. The micro-instruction specifies one or more micro-operations for the system. A sequence of micro-instructions constitutes a microprogram. Since alterations of the microprogram are not needed once the control unit is in operation, the control memory can be a read-only memory, ROM. The content of the words in ROM are fixed and cannot be altered by simple programming since no writing capability is available in the ROM. ROM words are made permanent during the hardware production of the unit. The use of a microprogram involves placing all control variables in words of ROM for use by the control unit through successive read operations. The content of the word in ROM at a given address specifies a micro-instruction. A more advanced development known as dynamic microprogramming permits a microprogram to be loaded initially from an auxiliary memory such as a magnetic disk. Control units that use dynamic microprogramming employ a writable control memory. This type of memory can be used for writing to change the microprogram but is used mostly for reading. A memory that is part of a control unit is referred to as a control memory. A computer that employs a microprogrammed control unit will have two separate memories, a main memory and a control memory. The main memory is available to the user for storing the programs. The contents of main memory may alter when the data are manipulated and every time that the program is changed. The user's program in main memory consists of machine instructions and data. In contrast, the control memory holds a fixed microprogram that cannot be altered by the occasional user. The microprogram consists of micro instructions that specify various internal control signals for execution of register micro operations. Each machine instruction initiates a series of micro instructions in control memory. These micro instructions generate the micro operations to fetch the instruction from main memory, to evaluate the effective address, to execute the operation specified by the instruction, and to return control to the fetch phase in order to repeat the cycle for the next instruction. The general configuration of microprogrammed control unit is demonstrated here in the block diagram. The control memory is assumed to be a ROM, within which all control information is permanently stored. The control memory address register specifies the address of the micro instruction, and the control data register holds the micro instruction read from memory. The micro instruction contains a control word that specifies one or more micro operations for the data processor. Once these operations are executed, the control must determine the next address. The location of the next micro instruction may be one next in sequence, or it may be located somewhere else in the control memory. For this reason, it is necessary to use some bits of the present micro instruction to control the generation of the address of the next micro instruction. The next address may also be a function of external input conditions. While the micro operations are being executed, the next address is computed in the next address generator circuit and then transferred into the control address register to read the next micro instruction. Thus, a micro instruction contains bits for initiating micro operations in the data processor part and bits that determine the address sequence for the control memory. The next address generator is sometimes called a microprogrammed sequencer, as it determines the address sequence that is read from control memory. The address of the next micro instruction can be specified in several ways depending on the sequencer inputs. Typical functions of a microprogrammed sequencer are incrementing the control address register by 1, loading into the control address register an address from control memory, transferring an external address, or loading an initial address to start the control operations. The control data register holds the present micro instruction while the next address is computed and read from memory. The data register is sometimes called a pipeline register. It allows the execution of the micro operations specified by the control word simultaneously with the generation of the next micro instruction. This configuration requires a two-phase clock, with one clock applied to the address register and the other to the data register. The system can operate without the control data register by applying a single-phase clock to the address register. The control word and next address information are taken directly from the control memory. It must be realized that a ROM operates as a combinational circuit, with the address value as the input and the corresponding word as the output. The content of the specified word in ROM remains in the output wires as long as its address value remains in the address register. No read signal is needed as in a random access memory. Each clock pulse will execute the micro operations specified by the control word and also transfer a new address to the control address register. In the example that follows, we assume a single-phase clock and therefore we do not use a control data register. In this way, the address register is the only component in the control system that receives clock pulses. The other two components, the sequencer and the control memory, are combinational circuits and do not need a clock. The main advantage of the microprogrammed control is the fact that once the hardware configuration is established, there should be no need for further hardware or wiring changes. If we want to establish a different control sequence for the system, all we need to do is specify a different set of micro instructions for control memory. The hardware configuration should not be changed for different operations. The only thing that must be changed is the microprogram residing in control memory. It should be mentioned that most computers based on the reduced instruction set computer architecture use hardwired control rather than a control memory with a microprogram.